quiet archive record. Tonight, we cross into a quiet world where the dark is safe and the story is enough. Let the day fade away and quietly slip into the deep. Phoenix. A is a black hole that shows up in a record book for one reason. It is one of the biggest black holes we have strong evidence for. But the phrase biggest black hole can mean a few different things. Mass is one kind of big. The width of the event horizon is another kind of big. And the reach of its gravity out into the space around it is big in a different way again. The goal here is to pin down what Phoenix A is, where it sits in the universe, how its mass is estimated, what its event horizon size could be, and how it compares to famous giants like the black hole in the Milky Way and the one in the galaxy M87. Tonight, we explore how big Phoenix A is. Start with the basic question. What is Phoenix A? Phoenix A is a name given to the central galaxy in a very large cluster of galaxies. The full cluster is often called the Phoenix cluster. In astronomy, a galaxy cluster is like a city made of galaxies. A single galaxy, like the Milky Way, can have hundreds of billions of stars. A cluster can have hundreds or even thousands of galaxies, and most of the mass in a cluster is not even in stars. A huge amount is in hot gas spread between the galaxies, plus dark matter that we cannot see directly. In the very center of many large galaxies, there is a supermassive black hole. Our own galaxy has one. It is called Sagittarius A star, and it has a mass of about 4 million suns. That sounds massive, but 4 million suns is small compared to the monsters at the centers of giant galaxies. Phoenix A is the name used for the black hole at the center of the central galaxy of the Phoenix cluster. When people talk about Phoenix A in the way we are using it here, they are usually talking about that central black hole. So when we ask, how big is Phoenix A? We are asking, how massive is that black hole? And also, how large is its event horizon? And, in a wider sense, how huge is the whole system around it that this black hole lives in? To keep things simple, we will focus on the black hole itself, but we will keep the surrounding cluster in view, because the environment matters. A black hole does not sit in empty space. It sits in a galaxy. The galaxy sits in a cluster, and the cluster is full of gas that can feed the black hole. Now we need to address a key point that trips up a lot of people. A black hole is not like a rock or a ball with a solid surface. A black hole is defined by a boundary called an event horizon. The event horizon is the point of no return. If something crosses it, it cannot get back out, not even light. When we say a black hole is big, we usually mean it has a large mass. But the event horizon size depends directly on mass too. The more mass, the larger the event horizon. There is a simple rule for a non-spinning black hole that is useful as a comparison tool. The radius of the event horizon, called the Schwarzschild radius, is about 3 kilometers for one solar mass. One solar mass means the mass of our sun. So a black hole with the mass of the sun would have an event horizon radius of about 3 kilometers. That is roughly the distance across a small town. A black hole with 10 solar masses would have a radius of about 30 kilometers. That is like the distance across a large city. A black hole with 1 million solar masses would have a radius of about 3 million kilometers. That is a few times the distance from Earth to the Moon. And a black hole with 1 billion solar masses would have a radius of about 3 billion kilometers. That is about 20 astronomical units, where 1 astronomical unit is the distance from Earth to the Sun. 20 astronomical units is around the orbit of Uranus. This rule is not perfect for a spinning black hole, and most real black holes spin. But it is a good first approximation. It gives you a way to turn mass into a size you can imagine. So the key question becomes, what is the mass of Phoenix A? Different studies and methods give different estimates, but Phoenix A has been suggested to be around tens of billions of solar masses. You will often see a number near 100 billion solar masses mentioned in popular summaries. That number is not as solid as the 4 million solar masses for Sagittarius A star, but it is not made up either. It comes from combining several clues. A careful way to say it is this: Phoenix A is a candidate for an ultramassive black hole, maybe in the range of tens of billions of solar masses, and some interpretations push it toward around 100 billion solar masses. That is so far beyond normal human scale that it is hard to feel it in your bones. So we are going to build a ladder of comparisons. First rung, our Sun. If you imagine the mass of the Sun as a 1 kilogram weight, then the mass of Phoenix A at 100 billion solar masses would be 100 billion kilograms. That is 100,000 kilograms. But a kilogram is not a great unit to feel either. So try this. If the Sun is a single grain of sand, Phoenix A would be a mountain range made of sand grains. Now second rung, Sagittarius A star. Sagittarius A star is about 4 million solar masses. If Phoenix A is 100 billion solar masses, then Phoenix A would be about 25,000 times more massive than Sagittarius A star. If Sagittarius A star were a full-grown elephant, Phoenix A would be a mass like a whole herd of elephants the size of a continent. Not a neat comparison, but it points to how far apart they are. Another way, if Sagittarius A star were the weight of a large cargo ship, Phoenix A would be the weight of tens of thousands of cargo ships. Third rung, M87 star. The black hole in the galaxy M87, the one whose image was released by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses. If Phoenix A is 100 billion solar masses, it would be about 15 times more massive than M87 star. That alone is a striking idea, because M87 star already looks gigantic when you compare it to our black hole. Fourth rung, Ton 618. Ton 618 is a famous quasar black hole estimate, sometimes given as around 66 billion solar masses, though the uncertainty is large. If Phoenix A were near 100 billion solar masses, it would be bigger than Ton 618, at least by some mass estimates. So Phoenix A sits in the rare category where the numbers stop being large and start being absurd. At these extremes, the measurements are indirect and the estimates can spread out. So how do astronomers estimate the mass of a black hole so far away? One method is to look at the motion of stars or gas close to the black hole. For nearby black holes like Sagittarius A star, we can watch stars orbit the center over many years. We can measure their speeds and their paths, and infer the mass that must be there to hold them in orbit. For very distant black holes, we cannot usually see individual stars moving. It is like trying to watch a single person walking around a campfire from the other side of the Earth. The person is too small. You see the glow, but not the steps. So for distant systems, astronomers use indirect methods. One common approach is based on the link between a galaxy and its central black hole. In many galaxies, the mass of the black hole is related to the properties of the galaxy bulge, the dense central region of stars. There is a relationship between black hole mass and the velocity dispersion of stars in the galaxy bulge. Velocity dispersion is a fancy term for how fast the stars are moving around in random directions. Imagine a swarm of bees. If the bees are flying slowly, the swarm is calmer. If they are buzzing fast, the swarm is more energetic. In a galaxy bulge, the stars move in a kind of gravitational swarm. The faster the stars move, the deeper the gravitational well must be. This relationship, often called the M-sigma relation, is not perfect, but it gives a way to estimate black hole mass from galaxy measurements. Another method uses the brightness of the galaxy and the size and structure of its bulge. In some cases, if the galaxy is extremely massive, the relation suggests an extremely massive black hole. For Phoenix A, the central galaxy is an enormous, very bright, very massive galaxy at the center of a powerful cluster. That fact alone hints at a very massive black hole. But there is more. Phoenix A sits in a cluster with a huge amount of hot gas. In many clusters, the central black hole helps control the cooling of that gas through jets and outbursts. The black hole can act like a thermostat. If the gas tries to cool and fall inward, it can feed the black hole. The black hole then blasts energy back out through jets, heating the gas and slowing the cooling. In the Phoenix cluster, the cooling and star formation rates are extreme. It is one of the most star-forming cluster central galaxies known. That suggests the usual thermostat is not working the same way, or it is overwhelmed. That kind of environment can mean a lot of gas is flowing toward the center. And if a black hole has a deep enough gravitational pull, it can grow very large. So some studies have looked at Phoenix A and asked, if this system has grown this huge, what does that say about its black hole? Now, before we get lost in the details, we should pause and deal with a common misunderstanding. People often think of black holes as giant vacuum cleaners that suck everything around them. In reality, if you replace the sun with a black hole of the same mass, the planets would orbit the same way. Gravity depends on mass, not on whether the mass is in a star or a black hole. The special thing about a black hole is what happens very close to it. The event horizon is a one-way boundary. So Phoenix A being big does not mean it is pulling on the entire cluster like a cosmic magnet. The cluster is held together mostly by dark matter on huge scales. The black hole is a tiny point in the middle by size, even if it is massive. This is another place where analogies help. Imagine a sports stadium filled with people. The black hole is like the person in the very center holding a heavy bowling ball. Compared to the whole stadium, the bowling ball is heavy, but it does not control the motion of everyone in the stands. It mostly affects the person holding it and the people within a few steps. In a galaxy, the black hole can strongly affect the inner region. It can shape gas flows, launch jets, and change star formation. But the outer parts of the galaxy and the cluster as a whole are dominated by much larger scale mass. So the question, how big is Phoenix A, is not about how far its gravity reaches. It is about how much mass is packed behind that horizon and what kind of horizon size comes with it. Let us convert the mass estimate into an event horizon size. Use the 3 kilometers per solar mass rule for the radius. If Phoenix A is 100 billion solar masses, the event horizon radius would be about 3 kilometer times 100,000 das, 300,000 kilometers. That is 300 billion kilometers. Now we need a sense of scale. The distance from Earth to the Sun is about 150 million kilometers. So 300 billion kilometers is 300,000 million kilometers. Divide by 150 million, and you get about 2,000. So the radius would be around 2,000 astronomical units. That means the diameter would be about 4,000 astronomical units. What is 4,000 astronomical units in terms of the solar system? Pluto is around 40 astronomical units from the Sun. The Kuiper belt is roughly in that range. The inner Oort cloud might start a few thousand astronomical units out. So a 100 billion solar mass black hole would have an event horizon diameter that could be comparable to the scale of the inner Oort cloud. Not the whole Oort cloud, which can extend tens of thousands of astronomical units, but still very far beyond the planets. That is an extreme mental picture. If you placed Phoenix A at the center of our solar system, its event horizon could swallow the Sun, all the planets, and reach out thousands of times farther than Earth is from the Sun. But remember, this is a rough estimate. If the mass is lower, say 30 billion solar masses, then the horizon size would scale down by the same factor. At 30 billion solar masses, the radius would be 90 billion kilometers, and the diameter would be 180 billion kilometers. That is still huge. It is still far beyond Pluto. So either way, Phoenix A is in the class of black holes where the event horizon could be larger than the scale of our planetary system. Now another key point. When people hear these size comparisons, they sometimes imagine a black hole as a giant dark sphere moving through space like a planet. That is not how it works. The event horizon is a boundary in space, not a solid surface, and black holes do not have a material shell. If you fell toward the event horizon, you might not notice the exact moment you crossed it, depending on the black hole size and your point of view. The physics close to the horizon is intense, but the boundary itself is not a wall. In fact, for very large black holes, the tidal forces at the horizon can be smaller than for small black holes. Tidal forces are the stretching forces caused by gravity being stronger on one side of you than the other. This gives us another comparison. A small black hole, like one a few times the Sun's mass, has very strong tidal forces at its horizon. It would stretch you like taffy long before you reach the horizon. A supermassive black hole can have a horizon so large that the tidal forces at that boundary are much weaker. If you cross the horizon of a very massive black hole, you would not be torn apart at that exact moment. You would still be doomed, but the spaghettification could happen deeper in. So a huge black hole is big, not just in mass, but in how it changes the local environment. Now, if Phoenix A is so massive, why is there uncertainty? Because we do not have a clean, direct measurement like we do for Sagittarius A star. Phoenix A is far away. It is located in a cluster billions of light years from us. At that distance, our instruments see the central galaxy as a bright blob with details, but we cannot track individual star orbits. We must infer, and the relationships we use to infer, like the M-sigma relation, were built mostly on closer galaxies, with black holes in the range of millions to a few billion solar masses. When you push those relations to the extreme end, you are like someone using a bathroom scale to weigh a truck. You might get a number, but the scale might not be designed for it. This does not mean the estimate is worthless. It means it has wider error bars. So the best way to talk about Phoenix A is not to cling to one number. The best way is to say it is a top-tier candidate for an ultra-massive black hole in the tens of billions of solar masses range. with some estimates reaching toward around 100 billion. Now, to make the story feel grounded, we should walk through what it means to compare masses at these scales. Think about the Milky Way. The Milky Way has a total mass, including dark matter, of maybe around 1 trillion solar masses. The exact number depends on how far out you count and how you measure. If Phoenix A is 100 billion solar masses, then the black hole alone would be around 1/10 the mass of the Milky Way's entire galaxy in stars and gas, not counting dark matter. That sounds almost impossible, because we are used to the idea that black holes are tiny compared to their galaxies. In many galaxies, the black hole mass is around 0.1% of the bulge mass, not 10% of a whole galaxy. So if a black hole is truly 100 billion solar masses, it pushes the usual rules. It might mean the galaxy is also extreme, or it might mean the estimate is on the high end. Either way, it tells you that Phoenix A sits at the edge of known trends. Now consider another angle. How do we talk about size? If the black hole itself is invisible, we can talk about the sphere of influence. The sphere of influence is the region where the black hole's gravity is the main driver of how stars move. Outside that region, the gravity of the galaxy's stars and dark matter becomes dominant. For Sagittarius A star, the sphere of influence is a few light years. For M87 star, it is much larger. For an ultra-massive black hole, it could be enormous. If Phoenix A is tens of billions of solar masses, its sphere of influence could reach tens of thousands of light years, depending on the galaxy structure. To make that vivid, picture a city again. The black hole is the city center. The sphere of influence is like the downtown where the rules are set by the center. Farther out, you enter suburbs where the city is still there. But the center is less controlling. For a normal supermassive black hole, downtown might be a few blocks. For an ultra-massive one, downtown might stretch across the whole city. This is part of why these objects matter. They are not just bigger versions of smaller black holes. They can change the way a galaxy evolves. Now we should talk about Phoenix A's location and why it became famous. The Phoenix cluster is known because it has a very large amount of hot gas that is cooling rapidly, and because its central galaxy is forming stars at a high rate. In many clusters, the central black hole prevents too much gas from cooling because it injects energy through jets. This is often described as feedback. The black hole and the gas form a loop. Gas cools and falls in. The black hole feeds. The black hole launches jets. The jets heat the gas. The cooling slows. That keeps the cluster from turning all of its gas into stars too quickly. In the Phoenix cluster, it seems like the gas is cooling fast anyway. This suggests the feedback is either temporarily weaker or the cooling is unusually strong. In either case, the center is a busy place. And a busy center can grow a big black hole. So Phoenix A is not just a random black hole. It is a black hole in a system that looks like it is in an active growth phase. Now let us make the scale of a galaxy cluster feel real. A cluster can be millions of light years across. A light year is about 9.46 trillion kilometers. So even 1 million light years is about 9.46 quintillion kilometers, which is a number too large to hold in your head. A better comparison is time. If you could travel at the speed of light, it would take 1 million years to cross 1 million light years. We cannot do that. So instead, we use the cluster scale to understand how tiny a black hole horizon is, even when it is gigantic. If Phoenix A has a horizon diameter of thousands of astronomical units. That is maybe a tiny fraction of a light year. 1 light year is about 63,000 astronomical units. So even a 4,000 AU horizon is only about 0.06 light years across. That means even an ultra-massive black hole has a horizon that is smaller than a tenth of a light year. Now compare that to a galaxy, which is tens or hundreds of thousands of light years across. And compare that to a cluster, which is millions of light years across. So Phoenix A can be huge, yet still be a microscopic dot compared to its cluster. This is another useful analogy. Imagine a continent as the cluster, a country as the central galaxy, a city as the region around the black hole, and a single building as the event horizon. The building can be the largest building ever built, but it is still not the continent. Now, a person might ask, if it is so far away and so hard to measure, why do we care? We care because black holes like Phoenix A test our models. Our models of galaxy growth say that black holes and galaxies grow together. We think black holes grow by swallowing gas and by merging with other black holes when galaxies merge. There are limits. There is only so much gas available. There is only so much time. So when we see a candidate black hole with a mass near 100 billion solar masses, it asks a tough question. How did it get that big? Did it grow early in the early universe when gas was more common? Did it go through many mergers? Did it live in an environment where feeding was unusually easy? Or is the estimate too high and the real mass is lower but still very large? These are not just trivia. They connect to the story of how structure in the universe formed. Now, to keep our feet on the ground, let us compare Phoenix A to a few other big names. Sagittarius A star, 4 million solar masses. M87 star, 6.5 billion solar masses. The black hole in Andromeda, around 100 to 200 million solar masses. The black hole in the galaxy NGC 4889, a famous giant in the Coma cluster, around 20 billion solar masses with uncertainty. The black hole in Holm 15A has also been discussed as a very massive candidate, Tana 618, often quoted around 66 billion solar masses. Phoenix A, discussed in the same breath as these, sometimes even bigger. What you should notice is this. Once you get above about 10 billion solar masses, the list gets short. There are not many well-measured examples. The uncertainties widen. This is like the difference between measuring the height of people in a room and measuring the height of mountains. People are all in a narrow range. Mountains vary more, and measuring them depends on maps and instruments. The bigger the target, the more your method matters. Now, there is another kind of big we can talk about: energy output. Some black holes are big in mass, but quiet. Others are big in mass and are actively feeding, producing bright radiation and jets. When a black hole is actively feeding, it can turn a portion of the mass energy of infalling matter into radiation. This can be extremely bright. In some cases, the black hole can shine brighter than the entire galaxy. Phoenix A is not mainly famous as a bright quasar, in the same way as Tun 618, but it sits in a system where the central environment is active. Still, brightness is not the best way to measure size. A smaller black hole feeding fast can be brighter than a larger black hole feeding slowly. That is another important point. Black hole size is mostly about mass, not brightness. Now let us talk about how people sometimes get confused between mass and volume. A black hole does not have a normal volume. The event horizon encloses a region, but the black hole interior is not like a normal space you can fill with matter. But you can still imagine the horizon as a sphere to get a sense of scale. If the horizon radius is thousands of astronomical units, the horizon volume would be enormous if you treat it like a sphere. But that does not mean it is filled with air or gas. It is a boundary. This is like a border on a map. The border encloses a country. The border itself is not a wall of stone. It is a line that defines what is inside. The event horizon is a boundary that defines what cannot escape. Now, another way to make the event horizon size feel real is to compare it to known distances. The average distance from the Sun to Neptune is about 30 astronomical units. If Phoenix A has a radius of 2,000 astronomical units, then the radius is about 67 times the distance to Neptune. That means the horizon diameter would be about 134 times the distance to Neptune. If you could place a string from the Sun to Neptune, and you had to lay that string end to end 134 times, that would be the horizon diameter. Another comparison. The distance from Earth to the Moon is about 384,000 kilometers. The horizon diameter for a 100 billion solar mass black hole, around 600 billion kilometers, would be about 1.6 million times the Earth to Moon distance. That number is silly. It does not help much. So a better comparison is to the solar system scale. Pluto is about 40 AU. The horizon diameter could be 4,000 AU. So the horizon could be about 100 times the orbit of Pluto. That is a good picture. Put Pluto's orbit as a ring. Multiply that ring size by 100. That is the event horizon diameter. Now, a person might ask, if it is so massive, would it swallow the galaxy around it? Not in the way people imagine. The black hole can only swallow what comes close to it. Most stars in a galaxy are on stable orbits far from the black hole. For a star to fall in, it needs to lose angular momentum, which is like the sideways motion that keeps it in orbit. That is not easy. Stars are like cars on a highway. They are all moving in their own lanes. They do not usually slam into the center. Gas is different. Gas can collide with itself, lose energy, and spiral inward more easily. So black holes grow more by gas feeding than by swallowing random stars. In a dense, gas-rich environment, like the center of a cluster, a black hole can have more chances to feed. Now let us talk about what we mean by Phoenix A being a black hole and not something else. We use the term black hole because the mass is concentrated and the evidence fits the idea of a supermassive black hole. There is no other known object that can pack that much mass into that small A region without shining like a star or exploding. So even when the mass estimate is uncertain, the object is still understood as a black hole. Now, to make sure the story stays easy to follow, we will organize the rest of the narration by answering a set of simple questions. 1. How far away is it, and what does that mean for our view? 2. What is the best mass range to keep in mind? 3. What would its event horizon size be in those cases? 4. How does it compare to other big black holes and to galaxies? 5. How could something like that form? And 6. What could future observations do to tighten the estimates? First, distance. The Phoenix cluster is at a redshift around 0.6, which corresponds to a distance of several billion light years. Depending on the cosmology you use, you do not need to memorize that number. The key point is that it is far enough that we see it as it was billions of years ago. That means Phoenix A is not just a huge black hole today. It was huge in the past, when the universe was younger. If it is truly near the top of the mass range, it suggests very fast growth. This matters because black holes need time to grow. A black hole can grow by feeding, but there are limits. If it feeds too fast, the radiation it produces can push gas away. So there is an idea called the Eddington limit, which is like a speed limit for black hole growth in many cases. If a black hole grows near that limit, it can increase in mass by a certain factor over a certain time. Starting from a small seed, it takes time to get to billions of solar masses. So getting to tens of billions early in the universe is challenging. This is one reason ultramassive black hole candidates are interesting. Now second, mass range. To keep the story honest, we will use a few example masses. Example A, 20 billion solar masses. Example B, 50 billion solar masses. Example C, 100 billion solar masses. These are not official numbers. They are guideposts. They let us see how the size scales. For 20 billion solar masses, horizon radius is about 60 billion kilometers. That is about 400 AU radius, 800 AU diameter. For 50 billion solar masses, horizon radius is about 150 billion kilometers. That is about 1000 AU radius, 2000 AU diameter. For 100 billion solar masses, horizon radius is about 300 billion kilometers. That is about 2000 AU radius, 4000 AU diameter. Even at 20 billion solar masses, the horizon diameter is far beyond Pluto. At 100 billion, it starts to feel like the edge of the inner Oort cloud. Now third, compare to other black holes. Sagittarius A star has a horizon radius around 12 million kilometers, because 4 million suns times 3 kilometers is 12 million kilon. That is smaller than the orbit of Mercury. So even though Sagittarius A star is 4 million suns, its event horizon would fit inside the inner solar system. M87 star, at 6.5 billion solar masses, has a horizon radius around 19.5 billion kilometers. That is about 130 AU radius, 260 AU diameter. So M87 star's horizon would cover a region larger than Pluto's orbit. Now compare that to Phoenix A at 50 billion solar masses. Phoenix A would have a diameter around 2000 AU. That is about 8 times larger in diameter than M87 star. At 100 billion solar masses, it would be about 15 times larger in diameter than M87 star. That is a huge jump. Now fourth, compare to galaxies. A galaxy like the Milky Way is about 100,000 light years across. 100,000 light years is about 6.3 billion astronomical units. So even a 4000 AU horizon is tiny compared to a galaxy. If the Milky Way were the size of Earth, the event horizon of Phoenix A would be like a small coin on the surface, but the coin would still be a coin with insane mass packed behind it. That comparison is useful. It tells you why the black hole can be central, but not dominate the whole galaxy by size. Now fifth, formation. How could a black hole get to tens of billions of solar masses? There are a few main ideas. One is that it started as a very large seed black hole. Instead of starting as a black hole made from one star, it might have started from a direct collapse of a large gas cloud, producing a seed of tens of thousands, or even more solar masses. That is like starting a savings account with a big deposit instead of starting with a few dollars. Another idea is that it grew through long periods of strong feeding. If the black hole had access to a steady supply of gas, it could grow faster. Another is that it grew by merging with other black holes. When galaxies merge, their central black holes can merge too. In a dense cluster environment, big galaxies can grow by swallowing smaller galaxies. Over time, the central black hole could merge with many others. This is like building a snowball by rolling it down a hill full of other snowballs. Each time you hit one, you get bigger. But merging has its own limits. The black holes must find each other and lose energy, often by interacting with stars and gas. That can take time. So the real story is probably a mix. A big seed, plus feeding, plus mergers. Phoenix A sits in a cluster center, which is a place where mergers and gas flows can happen. Now, sixth, future observations. How could we get a better mass estimate? The most direct method is still to measure motion close to the black hole. For nearby galaxies, we can do this by resolving stars or gas disks. For distant galaxies, we need extremely sharp instruments. Future telescopes, especially very large space and ground telescopes, could help measure the central regions better. We can also use gravitational lensing and cluster dynamics to understand the mass distribution around the central galaxy. And we can compare multiple scaling relations and see if they agree. If different methods converge on a very high mass, our confidence rises. If they disagree widely, then we know we are still guessing too much. Now, let us take a slower walk through the idea of big, using a set of everyday comparisons that stay honest. Imagine you have three objects: a marble, a bowling ball, and a small car. They all can fit in a garage, but their mass and their effect on you are different. A marble is easy to move. A bowling ball takes effort. A car is heavy enough that you need special tools. Now imagine that the garage is a galaxy center. Sagittarius, a star, is like the bowling ball. M87 star is like the car. And Phoenix A, if it is near the top estimates, is like a whole building. It still sits in the same garage area, the central region of a galaxy, but its weight is in a new category. Another comparison is to Earth itself. Earth has a mass of about 6 times 10 to the 24 kilograms. The Sun has a mass of about 2 times 10 to the 30 kilograms. So the Sun is about 333,000 Earths. If Phoenix A is 100 billion suns, it is about 100 billion times 333,000 Earths. That is 3.33 times 10 to the 16 Earth masses. That number is too big to feel. So change the comparison. If Earth were a single drop of water, the Sun would be a swimming pool. Phoenix A would be a chain of swimming pools filling a whole region. Not a perfect picture, but again, it tells you this is not just a slightly larger black hole. It is a different class. Now, we should also talk about what Phoenix A is not. Phoenix A is not a hole in space like a tunnel. It is not a portal. It is not a place you can travel through. In science fiction, black holes are often used as doorways. In real physics, a black hole is a region where gravity is so strong that escape is not possible once you cross the horizon. The size we are talking about is the size of that horizon. Now, if the horizon is thousands of AU across, that sounds like a vast region. But space is mostly empty. If you traveled through a region that size, you would still see mostly darkness, unless there was gas and stars around. The horizon itself would not look like a solid black ball. It would be defined by what light can escape. If the black hole is feeding, you might see a bright disk of hot gas around it. If it is launching jets, you might see jets. But the horizon would still not be a surface. Now, let us bring in an important detail about Phoenix A as a system. The Phoenix cluster is known for being a cluster with a huge cooling flow. Hot gas in clusters is so hot that it shines in X-rays. X-ray telescopes can map this hot gas. If the gas cools, it can fall inward. In many clusters, we do not see as much cooling as we would expect. The black hole feedback seems to prevent it. But in Phoenix, the cooling is strong. That suggests a large amount of gas could be available. If a black hole is in a place with lots of gas, it can grow. This does not guarantee a 100 billion solar mass black hole, but it fits the idea that the center is extreme. Now we can also talk about the central galaxy. The central galaxy in a cluster is often called the brightest cluster galaxy, or BCG. BCGs are some of the biggest galaxies in the universe. They often have huge halos of stars. They have grown by merging many smaller galaxies. So a BCG is like a downtown area that has absorbed many towns around it. If Phoenix A's central galaxy is huge, it makes sense that its black hole could be huge. But again, we have to be careful. The biggest galaxies are rare, so the scaling relations are less tested there. Now, a good way to stay balanced is to talk about the evidence categories. Category 1. The central galaxy is extremely massive. Category 2. The environment suggests strong gas inflow and activity. Category 3. Scaling relations predict a very large black hole. Category 4. The mass estimate is not directly measured by resolved orbits. So the estimate is exciting, but not as tight as nearby measurements. Now let us turn to a simple, concrete question. If you could stand far away and look at Phoenix A, what would you see? You would see a galaxy in the center of a cluster. You would not see the black hole directly, but you might see clues. You might see a bright central region where stars are forming. You might see jets in radio images. You might see X-ray cavities, which are bubbles in the hot gas made by black hole outbursts. These cavities are like dents in a fog bank carved out by a powerful blast. In some clusters, these cavities are huge. They show that the black hole injected a huge amount of energy. In Phoenix, the situation is complex, but a central system shows signs of strong activity. Now, another point. Sometimes people ask, is Phoenix A the largest black hole in the universe? The honest answer is no one can say that. We have many candidates. We have uncertainty. The universe is huge. It is more accurate to say Phoenix A is one of the best known candidates for a black hole at the top end of mass. There may be bigger ones. There may be smaller ones. The list is not final. Now, let us build one more comparison that helps with the mind-bending size. Consider the orbit of Earth, 1 AU. If the event horizon radius is 2000 AU, that is 2000 times Earth's orbital radius. If you could draw Earth's orbit as a circle on a piece of paper, and it was 1 centimeter in radius, then Phoenix A's horizon radius would be 20 meters in radius. 20 meters is the length of a swimming pool. So on that scale, the horizon would be like a pool, while Earth's orbit is a small circle. But then remember that the galaxy scale on that same map would be enormous. The paper would not be big enough. So again, the black hole is huge by solar system standards, but still small by galaxy standards. Now let us talk about the word phoenix. The Phoenix cluster was named after the myth bird, the phoenix, that rises from ashes. The cluster is named that way because of the intense star formation and the idea of something being reborn in a place where it was expected to be quiet. That is a poetic framing. But our story will keep the focus on the physical facts. The physical fact is that the center is producing stars at a high rate. That means gas is cooling and condensing, and that can mean fuel is present. Now we can zoom into the black hole itself. and talk about what it means to have such a large mass. A black hole mass of tens of billions of solar masses implies a very deep gravitational well. It implies that the central region of the galaxy could have very high orbital speeds. It implies that the black hole can bind gas strongly. It implies that the energy released when gas falls in can be enormous. But it does not imply the black hole is actively eating everything at once. It can be massive and quiet, or massive and active. The activity depends on feeding. Now imagine a fire. The black hole mass is like the size of the fireplace. The feeding gas is like the wood supply. A huge fireplace with no wood is dark. A smaller fireplace with lots of wood can blaze. So mass and brightness are related, but not the same. Now let us address the last part of the question in a simple way. If you want a one-line answer, it would be something like this. Phoenix A is a candidate for a black hole with a mass in the tens of billions of suns, possibly near 100 billion, which would give it an event horizon diameter on the scale of thousands of astronomical units. But a story like this is better when you feel the comparisons. So we will keep going and fill in the picture. Let us talk about the difference between a black hole's mass and a black hole's size in a more physical way. Mass is how much gravity it has. The event horizon size is the radius where escape becomes impossible. If you double the mass, you double the horizon radius. So in that sense, mass and horizon size are directly connected. But what about density? Density is mass divided by volume. For a black hole, if you take the mass and divide by the volume inside the horizon, you get an average density. This is not a perfect concept, but it gives an interesting result. As a black hole gets more massive, its average density can go down. A stellar mass black hole can have an average density far higher than water. A supermassive black hole can have an average density comparable to water or even lower. That seems weird. How can something be a black hole if its density is low? The answer is that the black hole condition depends on how much mass is inside a given radius, not on a normal material density. A huge black hole spreads its mass over a huge horizon volume, so the average density can be low even though it is still a black hole. This means a black hole like Phoenix A, if extremely massive, could have an average density that is not insanely high by everyday standards. It is still an extreme object, but the geometry changes the intuition. This is a good analogy point. Imagine a person holding a pile of sand in a small bucket. If the bucket is small, the sand is packed tight. If you pour the same sand into a huge swimming pool, it becomes a thin layer. The amount of sand is the mass. The pool is like the horizon volume. A bigger black hole is like a bigger pool. The same packing idea changes. Now do not take this too literally. It is just a way to break the black holes are infinitely dense balls picture. Black holes do have a singularity in classical theory, but the event horizon and the size we talk about is different. Now, let us consider another comparison. The gravitational time effects. Close to a black hole, time runs differently compared to far away. Near the horizon, time dilation is strong. This is real physics. It is part of general relativity. But again, it matters mainly near the horizon. For Phoenix A, the horizon is huge, but the experience near it depends on your path. We are not going to drift into science fiction. We will keep this as a simple fact. Gravity affects time, and near very massive black holes, the effects can be strong close to the center. Now, to bring the story back to observation, we can ask, could we ever image Phoenix A's event horizon like M87's star? In practice, it is very hard. Even if the black hole is enormous, the cluster is very far away. Angular size matters. Angular size is how big something looks on the sky. A small object nearby can look bigger than a huge object far away. A coin held close to your eye can cover the moon. This is a perfect analogy. The moon is huge, but it is far. The coin is tiny, but it is close. So even if Phoenix A has a horizon larger than M87's star, it can still look smaller on the sky because it is farther away. That is why imaging the horizon is so hard. So we rely more on indirect clues. Now, let us consider the role of jets and radio observations. Many supermassive black holes launch jets. These jets can extend far beyond the galaxy. They can inflate bubbles in the hot gas. The power of the jets can tell you something about how much energy the black hole is releasing. But jet power does not directly give you black hole mass. A smaller black hole can have strong jets. A larger black hole can have weaker jets. It depends on feeding and magnetic fields. So jet observations are part of the story, but not the final measuring tape. Now we should talk about why Phoenix A is often mentioned with a number like 100 billion. In some discussions, astronomers use the mass of the central galaxy and a scaling relation to infer a black hole mass. If the galaxy is extremely large, the relation can yield an extreme black hole. But the relation might not be linear at the top end. It might bend. This is like a rule of thumb for car speed and engine size. It might work for small cars and medium cars, but for giant trucks, the rule changes. So a mass estimate at the extreme could be overestimated if the relation is pushed too far. That is why you will see different numbers. Some will say tens of billions. Some will say close to 100. The truth might be somewhere in between, but even the lower end is still enormous. Now, let us do a grounded comparison using the Milky Way again. If you took all the stars in the Milky Way and squeezed them into a black hole, you would get a black hole of around tens or hundreds of billions of solar masses, depending on the exact mass you count. So 100 billion solar mass black hole is like the mass of a large galaxy's stars, compressed into a black hole. That is a strong statement. It tells you how extreme it is. Now imagine the Milky Way as a crowd. Each star is a person. The black hole mass of Phoenix A is like taking a huge fraction of that crowd and packing it into one hidden core. It is not a perfect picture because black hole mass is not stars, but it shows the scale. Now we can also bring in the idea of accretion disks. If Phoenix A is feeding, gas falls in and forms a disk. The disk heats up. It can shine. The disk size can be much larger than the horizon, so the visible region around a black hole can be much bigger than the black hole itself. This is like a campfire again. The fire is the visible glow. The horizon is the invisible boundary inside. The glow can stretch far. Now, for a cluster center, the environment includes hot gas, cold gas, dust, and stars. A lot of complex physics happens, but our focus remains on the size question. So let us keep returning to the core numbers. Phoenix A likely has a mass in the tens of billions of solar masses. This puts its event horizon diameter in the range of hundreds to thousands of astronomical units. At the highest suggested mass, it could be several thousand AU across. This is large enough that if it were placed in our solar system, it would swallow all planetary orbits and reach far beyond. That is the most direct way to picture how big. Now, we can ask another simple question. How does that compare to a star? A star like the Sun has a radius of about 700,000 kilometers. Phoenix A's horizon radius at 100 billion solar masses could be 300 billion kilometers. That is about 400,000 times the radius of the Sun. So if the Sun were the size of a grape, Phoenix A's horizon could be the size of a city. Again, not perfect, but it gives a feel. Now let us talk about what happens if you orbit such a black hole. Far from the horizon, orbits can be stable. Close to the horizon, there is a last stable orbit. Inside that, matter plunges in. For a supermassive black hole, the last stable orbit is a few times the horizon radius. So the region where the most energetic disk action happens is still within a small multiple of the horizon. So if the horizon is thousands of AU, the disk could have intense action in a region of tens of thousands of AU. That is still small compared to a galaxy, but it is enormous compared to our solar system. Now we can connect this to another comparison. If the solar system was scaled up so that Earth's orbit was the size of a basketball court, then Phoenix A's horizon could be the size of a whole neighborhood. These comparisons are rough, but they keep the scale alive. Now, before we move deeper into growth and measurement, we should address one more confusion. People sometimes confuse black hole mass with the mass of the whole galaxy cluster. The Phoenix cluster has a mass far larger than the black hole, likely on the order of 1,000,000 billion solar masses or more. So the black hole is still a tiny fraction of the cluster. The cluster is the main mass system. The black hole is a concentrated center. So the black hole is like the densest point, but not the main weight. This matters because it stops the story from becoming the black hole controls everything. It does not. It influences the center. The cluster is held by much larger scale mass. Now let us talk about the idea of a record holder. The universe is a big place. We have only observed a small portion in detail. So anytime we say something is the largest, it is really largest we have seen and measured well enough. This is like saying a certain tree is the tallest in a national park. It might be, but there could be a taller tree in another forest that no one has measured yet. So Phoenix A is a candidate for an extreme black hole, not a final champion. Now let us return to measurement again and go step by step. If we want a direct mass, we would like to see stars orbiting, but we cannot. So we use galaxy properties. We measure how bright the galaxy is. We estimate its stellar mass. We measure velocity dispersion if possible. We fit scaling relations. We get a mass estimate. At each step, there is uncertainty. Brightness depends on distance and dust. Stellar mass depends on models of star populations. Velocity dispersion depends on resolution. Scaling relations have scatter. So the final mass can vary. This is why different studies can disagree. But even with disagreement, the conclusion can be stable. Phoenix A is extremely massive. Now, to keep our analogies balanced, let us use one more concrete comparison with something familiar. Consider the Great Pyramid of Giza. It has a mass of about 6 million tons, which is 6 billion kilograms. If you imagine the Sun as a pyramid, Phoenix A as 100 billion suns would be 100 billion pyramids. That is an impossible stack. So again, the number is too large. Instead, use relative comparisons. Phoenix A could be tens of thousands times more massive than our black hole. It could be more than 10 times more massive than M87 star. those ratios are easier to hold. Now, another interesting question is this. If the horizon is so large, could a star orbit inside the horizon size? No. The horizon is the boundary. Inside it, no stable orbit is visible to the outside. But could stars orbit close to it? Yes. In the central region of a galaxy, stars can orbit the black hole. Their speeds would be high. If we could measure those speeds, we could get a direct mass. That is what we do for nearby black holes. For Phoenix A, the distance makes it hard. Now let us connect to the cluster story again. The Phoenix cluster is filled with hot gas. Hot gas means X-rays. X-ray maps can show where the gas is dense and where it has been pushed around. When a black hole sends jets, it can carve cavities. These cavities can be measured. From the cavity size and pressure, we can estimate the energy of the outburst. This energy can be huge, but again, this is more about power than mass. Still, it tells us the black hole is active enough to shape its environment. Now, you might ask, can a black hole that big exist without tearing apart the galaxy? Yes. A black hole can sit in the center with stable orbits around it. The galaxy can exist. The main difference is that the central region, dynamics, and feedback can be extreme. Now, we can also talk about the idea of ultramassive black holes as a category. Most supermassive black holes are in the range of millions to a few billion solar masses. Ultramassive means above about 10 billion. If Phoenix A is truly above 50 or 100 billion, it would be at the far end of ultramassive. This could suggest there is a top end that depends on environment. Cluster centers might be the best places to find them, because cluster centers are where the biggest galaxies live, and where mergers happen, and where gas can pile up. Now, let us address a final practical question. If Phoenix A is that big, could it affect the motion of galaxies in the cluster? Not directly. The black hole gravity becomes weak at large distances compared to the total cluster mass. The motion of galaxies is set by the cluster dark matter halo. So Phoenix A does not pull galaxies like a hook. It shapes the gas and the central galaxy. Now, as we approach the end of this long explanation, it is worth repeating the core picture in plain words. Phoenix A is a black hole in the center of a giant galaxy, in the center of a giant galaxy cluster. It is so massive that it may be one of the largest black holes known. Its mass is likely in the tens of billions of suns, and some estimates suggest it could be near 100 billion. If it were near that top value, its event horizon could be thousands of AU across. That would make the horizon larger than the orbit of Pluto by a wide margin. But even so, it would still be tiny compared to the size of its galaxy and its cluster. That is the strange balance of black holes. They are huge by mass. They can be huge by horizon size. But the universe around them is bigger still. And that contrast is part of why they feel unreal. Now, one last comparison. If the entire solar system, out to Pluto, were a small ring on a table, Phoenix A's horizon could be a ring that covers the table and more. If the galaxy were a football field, the black hole would still be a tiny point in the center. Both can be true at once. That is how scale works in the universe. This was a quiet archive story, where the story ends, sleep begins,